Sounds a bit ominous. Good morning, everyone. Thanks so much for joining us. It's good to see you all. So this morning's speaker is Jeff Ridley. Jeff has a PhD from the University of Kent in satellite technology. After that, he did a postdoc in radar altimetry of ice sheets at the University College in London. Jeff predominantly works at the Met Office in the United Kingdom. He's published numerous important publications recently. Jeff's work is sort of generally interested in ice sheets, mountain glaciers, and their likely contribution to future sea level rise, so very relevant to our series. And I believe Jeff's recent work has been mainly in analysis of coupled models that incorporate a dynamic ice sheet component. With that said, if you could take over from here, Jeff, that would be wonderful. Thanks again for joining us.
Hi everyone. I'm going to be talking about the ice sheets in our current climate model, well, Earth system model, and this is something that's been going on for the last 5 years, putting these in, and several people have come and gone in that time, and my list of authors here is actually quite long. There's many people involved in just making the model work, the climate model work well enough. But I'm going to be focusing mostly on Antarctica because the Greenland ice sheet is easy to put into climate models, and about 20 GCMs have put in Greenland. But Antarctica is much more difficult, as I explained. But when I first started on this project, the question was asked, why? If you're interested in sea level rise, why would you put a couple global climate model, put one in an ice sheet into the global climate model? Because there's going to be no real adjustment or change in the ice sheet on a 100-year timescale. It increases complexity and runtime, which no climate model wants necessarily, particularly the runtime. So big efforts were put into consideration of the model runtime. Now, as I say, this is about Antarctica, and this map shows roughly the ice shelves and the important regions, which are the Bellinghausen and Amundsen Sea sectors, where the ice shelves are thinning rapidly, and it's believed from ocean warming. So you only need quite a small increase in temperature on these ice shelves, because the ice shelf water is already reasonably warm. So a small increase can cause a large melt rate at the base of the ice shelves. And but it could just be variability, and the water that's coming to these ice shelves is not young enough to be from global warming. So what do we need to consider with ice shelves? Why should we have explicit ice shelves in the model? And on the left here, we got different ways of parameterizing ice shelves, as well as the explicit ice shelf parameterization. So obviously the cavity forms its own water properties, but it's the meltwater we're interested in for sea level rise. And so we want to know whether any of these parameterizations do just as good a job with the same meltwater as the explicit ice shelf, same total meltwater. And so in the near field of the oceanography, in this middle plot, I'm sorry about people red-green colorblind, but here we're showing the barotropic stream function, which an impact of which is to draw up deep warm water onto the ice shelf itself. So you want this near field representation in any model, and you can see that the the top plot here shows what happens if you've got an actual ice shelf cavity, and you've got a stream function in front of the Pine Island Bay, which doesn't exist if you just put the surface water melt in a surface melt. So that stream function could be quite important in generating this melt. But if you parameterize the ice shelf as this ice shelf par, with the meltwater put in at the depth of the base of the ice shelf, then you also get that stream function appearing. And so the only place that there's a difference between this parameterization, the best parameterization, and the having explicit ice shelves, is in the Weddell Sea, where there's difference between all the parameterizations. And so we assume that the explicit one is correct. So this large cold shelf is different, whereas the Ross ice shelf, actually the near field isn't much different in any of them. So if we look at on the right, we've got profiles which are from a mooring in Pine Island Bay, and these show temperature and salinity, and you can see that the green and red lines are close to the black line, which is the mooring, whereas putting the shelf melt water into the surface, the blue line, is quite different. And so one might say, okay, the temperature salinity profiles are approximately the same with a parameterized shelf and a explicit ice shelf. So if we're interested in generating the representation of the ocean, we're probably going to do okay with a parameterized ice shelf. If we're interested in how do ice sheets work, then of course we can't. We've got to have the cavities. But if we're only interested in the oceanography, then it doesn't matter a lot. So how do we account for sea level rise at the moment? So the mass loss for ice sheets is calibrated to pre-industrial. So we have an equilibrium in pre-industrial times, and so we run the model for several hundred years and then take the average and of surface of total mass of the ice sheets, and make sure that doesn't change by setting the basal melt and the iceberg carving, and the surface melt, of course, is from the model. So that means that if you get more warming, you'll get more surface melt and therefore sea level rise. And but pretty much all else is held at constant. And the big problem is Antarctica. Antarctica gains mass, quite a lot of mass, and sea level goes down equivalent with increased precipitation. And everything else is constant because we don't know how to represent in a model without explicit ice shelves how these might change. So that's the first argument. The second argument is that there's been observations that the coastal current, the shelf break current that runs around Antarctica, can bring up warm intermediate water onto the surface depending on the wind stress. And that water, for example, can get under the Filchner ice shelf and cause temporary increases in melt. In fact, there was a big field campaign 4 or 5 years ago, which put a big effort into understanding the variability of the melt, with several moorings and observation core holes on the shelf. Now, models also indicate that this happens, and that in climate change simulations on the left, you can see that warm water is getting into the Filchner cavity, and that was attributed to surface stress, as the observations suggest. And as a consequence, the bottom plot here on the right is showing a massive increase in melt of the Ronnie filter and eventually, yeah, the Ronnie filter and ice shelf. And it's going up to 1,600 gigatons a year. And the current estimate of all the ice shelves around Antarctica is 1,500 gigatons. So this is going from practically nothing to all the equivalent to all the ice shelves, and in sometime this century. And it doesn't matter what scenario they ran, and they actually tried it with a different model with climate model data at the surface, and got the same result. So that was a fairly robust result, but not all models did this. And a more recent study shows that actually you get a freshening of the cavity. The what is known as the filtration trough in front of the filtration ice shelf. So you gradually, as you go through climate change, this is an abrupt 4 times CO2 experiment, which means you just step up to 4 times CO2 and run the model continuously at 4 times CO2, pre-industrial for CO2. And so you get in the section on the right on the left, the dotted lines is the pre-industrial control, and then you start the run, and the cavity gets fresher, and eventually it gets very fresh, and this results in a change because the warm saline water, which is in the circumpolar current, it now can't be stopped by saline water flowing off the continental shelf. And so that saline water now comes on to the shelf, just because due to density. And it pours onto the shelf and into the cavity as soon as the ice gets fresh enough. And this is attributed to the fact that sea ice, which normally causes the salinity of the shelf, carries the fresh water out beyond the shelf when it melts. But if the sea ice retreats, such that the melt and formation are on the continental shelf, there's no net change, and so the shelf just gets fresher and fresher, and until it can't stop the warm dense water coming on. However, I mean, these are interesting tipping points, and in fact, this this experiment by Caitlin Norton showed here that year 80 of the run, when the shelf water becomes fresh, is actually at 6 degrees warming. Whereas the previous paper, it occurred around about 2 degrees. So 6 degrees is a long time in the future, certainly not this century. And so it puts off the time where there might be a tipping point. And therefore, that tipping point is unlikely to occur in standard climate runs, which are just 100 years. But there's many different results of the Southern Ocean. It can be warm or cold in different climate models. And so the Southern Ocean is highly uncertain in climate models. If we tried to put ice shelf cavities and an ice sheet model, it could do almost anything in different models, depending on what biases there are in your model. And so is it actually worth doing until we've got better ocean in the Southern Ocean? Because even if we get the warmth in the wrong place, for example, then there's these unstable situations where you have marine ice sheet instability and marine ice cliff instability, which could be triggered depending on atmosphere and ocean biases. They might be triggered in the wrong in an unreasonable place. But so we could get things happening for the wrong reason. And it's these instabilities which have a large uncertainty in the sea level rise. So this is for different experiments, and if you've got ice cliff instability, then you've got a large uncertainty in sea level rise by 2300, say. But if you've only got marine ice sheet instability, which is the hatched lines, then it's slightly better. You've got more understanding of what's going to happen, depending on where you're warming. So perhaps it's not too bad if we're only able to simulate marine ice shelf instability. So the answer is that doing ocean-only simulations, ocean ice sheet simulations, or ocean ice sheet atmosphere simulations do not capture everything we want to do. So we really must have a complete coupled model to capture these rapid changes. And it hasn't been tried before in a coupled model, and so why not? So we then had to decide which of our family of resolutions we'd use. All the models all start from high resolution and are collapsed down to lower resolutions from that. So the high resolution is considered the truth as well as we can get it. And so if we look at these different resolutions of the ocean at the top, after 40 years of simulation, we can see that the low resolution model, which is on the left, has warm water on the shelf, and the cold ice shelves, Ross and Ronnie in particular, are cold, and so this is the bottom water. So that looks fine, but when you get to the intermediate resolution, the cold water, they're all cold ice shelves, and you can see why in the 12th degree resolution, which is about 3 kilometers at the Antarctic coast, that water is being pulled round from the cold Weddell Sea. It's going counterclockwise into the Bellinghausen Sea, and in the intermediate resolution, it's actually continued well into the Amazon Sea. So and it doesn't matter, at the bottom you have different atmosphere resolutions, and they make almost no difference. So it's definitely an ocean model resolution problem. But because of this, we figured, well, the low resolution is looking the best. Let's check some other things, and you can see that when you look at the barotropics.
Sorry, can I interrupt you 1 second? On the previous slide, could you, what's going on the bottom 3 panels? Is that like the same ocean resolution but different atmosphere resolutions?
Yeah, so this is the middle of the ocean resolution and different atmosphere resolutions.
Okay, sorry.
And okay, so the low resolution on the bottom. So this one in the middle is the ocean resolution, and we're putting different atmospheres on, seeing if it's any different, and perhaps there's a slightly better with the low resolution atmosphere, but this is really showing that it's an ocean model problem.
That's really interesting. And were you saying that you believe the climatology is better in the low ocean resolution than the medium or higher?
Yes.
Wow.
So the high resolution is eddy resolving. The intermediate resolution is eddy permitting, but the Rossby radius is nowhere near Antarctica in the intermediate resolution. Whereas in the high resolution, the Rossby radius is okay at 65 or 70 north south, but not right next to the ice shelves necessarily. But it's still not doing particularly well.
Yeah.
So the low resolution, of course, got parameterized eddies, and it's because of these parameterized eddies that things like this is a barotropic stream function, the gyres, and the Weddell gyre you can see is very deep, whereas most people think that the low resolution on the left is about the right gyre strength in terms of spherodraps, and the Ross Sea gyre has this extension towards the peninsula, whereas that doesn't happen in reality, and in fact the Orca 1, the low resolution, looks about right for the Ross Sea gyre, perhaps not quite strong enough, but the shape looks good. And so from this very strong Weddell Sea gyre, it's got a very steep gradient as you approach the peninsula, and it's that steep gradient which is pulling the cold water around the top and causing a counterflow against the ACC. It's only slightly improved in the high resolution. So when you actually look at the ACC strengths, all the models spin down. They spin down because the water on the shelf is freshening. And so the density gradient is what determines the ACC to some extent. And so these ones which are fresh and cold on the shelves are basically the medium resolution has a gyre half the strength of the low resolution, and the Orca 12 is still nowhere near right, and it's thought that the gyre strength is about 170. The ACC strength is 170. So the low resolution isn't bad, and so we figure, right, this definitely is producing the large scale circulation and large scale salinity about right. So we're going to stick with the low resolution. And this we call UK Earth System model, and with the ice sheets in IS. And this is a fully coupled ice sheet model, and the UK ESM is a community model with input from several select centres, for as you see below. The structure of this model and the ice sheets in this, the interface to the ice sheet is called unicycles, and that interfaces with the land surface scheme, which is as in the ice sheet is in the land scheme, and then interacts with the ocean physics, which is a model called NEMO. And then, of course, the mass balance of the ice sheet is determined by precipitation and melt from the atmosphere. So every time step the atmosphere. The mass balance is calculated from the atmosphere, and snow accumulates in the snow model, which is a Föhn model, effectively down to 10 meters, and under 10 meters, the temperature of the snow is pretty constant, and the density is almost ice. So we then interface when the snow gets to a certain depth. We interface with the ice sheet model and transfer the mass balance to the ice sheet. Obviously, the ice shelves are needed. They need the ocean and the treatment of the land is how the ice sheet is treated. There are other models in it, biogeochemistry and a dynamic vegetation model, but we consider the ice sheet to when it retreats from the land. The land is we consider to be just bare rock, so it's not colonized by any vegetation or biogeochemistry. And we actually switch off the marine geophysics because that is expensive. So now go through how this all works and how we've tried to solve some of the problems. So the ice sheet is sequential, which means that the model stops in order to execute the ice sheet. So the mass balance is calculated in the atmosphere, and if the snow depth is more than 10 meters, then mass is transferred to the ice sheet, the ice of the ice sheet, and so the surface elevation is actually the ice sheet surface elevation, not the snow surface elevation. If the snow depth is 0, then ice mass decreases because you're melting bare ice, and then after all this, the mass balance, the ice dynamics is calculated, and anything that crosses the border with the sea is then an iceberg. You then map back the ice model elevation, which is a high resolution model, back onto the model grid, which is a low resolution model, and the 7 different orography fields are updated. These are standard deviation and XX and YY linearity. So also we calculate that if there's no ice dynamics, i.e. that ice depth is less than 50 meters, then convert it all to snow. If all that snow melts, then we have a bare surface. Then after we've done that, we'll go back to restarting the atmosphere. And the atmosphere can stand quite considerable changes without to the surface topography. A couple of 100 meters before it starts to make a fuss about it. So the ice sheet model itself, not the interface, it's called bicycles, and it's on what's called an adaptive grid mesh. That means it's a square grid, but it can be refined, and it refines to the shear in the ice, the horizontal shear in the ice. So at the grounding line, there's very, very large difference in the shear, and so it needs very high resolution at the grounding line. But of course, the grounding line moves, so the adaptive grid follows the grounding line. But you don't want high resolution where the model is doing nothing interesting. in terms of shear. So it gets to a standard resolution, which is 8 kilometers, and we determined that about 2 kilometers was needed for the grounding line to adapt properly i.e. it will return to the same position if you change the forcing back again. This isn't a full stress model. It's what's called a 1.5 dimension model, in that it doesn't have vertical shear. It integrates up the vertical shear, and that cuts down the cost. So here's just a representation of what the model refinement of the grid is. I mean, this is actually a schematic rather than the actual grid size for Greenland and for Antarctica. So you can see the high resolution follows essentially the grounding line. So if we look at the how we do the surface mass balance, what we have is in the standard model without the ice sheet in it, every grid just has ice and snow, and the ice doesn't change and the snow melts when it needs to, and we initialize it with 1,000 meters of snow. This means that if we warm to 4 times CO2, we might melt 1,000 meters of snow. We're unlikely to, but it is possible. But in the new scheme, where you have, in order to better resolve the edges of the ice sheet, we actually have a hypsometry, which means that the energy balance, or the surface mass balance, is calculated on, in our case, 10 levels, but it's flexible. In the 10 levels in the atmosphere, up to the top of the ice sheet and down to the bottom, and which means we have to calculate the surface energy balance 10 times, which sort of increases the model runtime a bit. But each hypsometry is calculated separately. The only issue is that the clouds, you can't scale the clouds on level without messing up the model. The requirement being that this hypsometry, if you averaged it all out to the original grid, doesn't change the energy balance. And so you've got to conserve, and if you messed around with clouds, you wouldn't conserve. So we ignore the fact that the clouds would actually follow the surface rather than be at the mean level. Because in any climate, model conservation is absolutely key. So this what happens due to the hypsometry. So if you had no hypsometry, you'd have this bottom plot. So it'd be very blocky representative of the surface mass balance. And when you use the hypsometry and regrid to the ice sheet grid, which is on a different projection, you get a pretty good picture of the mass balance here. And if you zoom in on that, where the resolution is high at the ice boundary, you can see that actually there's a lot of detail here, and so the mass balance at the low level is melting and growing at the high level. So effectively, by having its hypsometry and interpolating it onto the model grid, is curing the problem of having a low resolution model. Going on to the interesting bit. So for the ocean coupled issue, you transfer the melt rate from the ocean to the bicycles, the ice sheet model, and that then calculates a new ice shelf draft after ice dynamics, and then you regrid back to the NEMO grid, and you have to do then some adjustments to the ocean mask and NEMO start dump before the ocean is restarted, because any change in grounding line, for example, without doing it, any adjustment will mess up the ocean and cause it to crash, because the ocean requires that the velocity, the perpendicular velocity at the grounding line has to be 0. And if you just move the grounding line, then something's happened and it's non-zero. So there's a lot of issues to solve here, and because we want the grounding line to move, we want the ice shelf base to melt and grow, and we'd rather like the ice shelf to advance, ice shelf front to advance and retreat. But as I'll explain later, that's currently not possible. So in fact, if the ice shelf melted from the bottom with strong warming, it will melt to about 10 meters, and we can't, and then we'd just say there's no more melt, because the atmosphere can't recognize that there's no ice shelf there. Needs major changes to the way the model works in order to solve this. But in any case, we have to make sure that all the balances work, and we do this with a partial cell. So there's normally in any ocean model, a Z-level model, Z-level model. Then at the bottom, as the orography changes, the bottom level of the model has to have partial levels to keep track of the bottom of the ocean, and so you do at the top as well. In this case, for the ice shelf interface. So rather, when you think of a Z-level model, it gets less and less resolved at lower, deeper and deeper into the ocean. And so at the grounding line, which is the most important part of the ice shelf, the model resolution might be quite coarse. The grounding line under, for example, the Filshner ice shelf is at about 4,000 meters. And down there is 70 meters between levels. So you're not getting a good resolution at the bottom. And so by having these partial cells, it allows the cell nearest the ice shelf to not be a full cell, but you can interpolate into it. But there's several issues to deal with here, because if you get part of, when you regrid the ice shelf back onto the ocean model, you can do all sorts of weird things, because the resolution is so much different than the actual ice sheet model, particularly the vertical resolution. So that means that you can be left with pockets of water in the ice shelf bottom, and you want to remove these pockets because water can't circulate in them, and anything that's less, only one grid cell has to be made in 2 grid cells in order to get the vertical velocity and horizontal velocity. So you've got the normal cell, and the partial cell is fine. So in this case, you've got to make sure that there's all wet cells underneath the ice shelf are connected, and that you remove, for example, lakes which are formed, because any the ocean still thinks it's part of the ocean and can't do any dynamical change with it, and it will crash. So
sorry to interrupt. We've got a question from Gary I've just noticed. He's asking, is there any
right.
Is there any mass? Yeah, he's trying to. Is there any mass being transferred to the surface? I.e., I'd expect a specific heat time.
Yeah, this is in the previous slide.
Ah, sorry.
Yeah.
That one.
No, that one there. So you got your thermodynamic there. There's no term for the specific heat times the basal temperature. If you're fluxing mass, then it has energy associated with the mass.
Yes. Sorry, that should be there. I mean, so there's a latent heat term.
Yeah. So there is, or this is just incorrectly written.
Yeah, it's incorrectly written at the moment.
Okay, no worries. Thanks.
Okay, so there also has to be conservation. If you move things around, the mass of the ice sheet must stay the same. So we have to make corrections for that. There's corrections for tracers in the ocean. You have to deal with that, and then of course the velocity. If you go from one geometry to another, you've got to shift mass from the ocean out further out, and so you get faster flow. Particularly if you've got to generate a partial cell, you actually have to move that water somehow out of that partial cell that's being created. So you do that by, in the first time step, creating a bigger flux. You don't just take that mass and put it across the whole ocean. We instead move it out of the cavity with this method. And then there's another type of problem, which is if you start off with a connected ocean and it becomes unconnected, generating a new cell, then obviously the model will collapse. But one way to solve this is to generate a virtual flux out of the model. And so it can connect things without actually moving ice shelf mass around. So this new geometry, virtual mass, is what happens in overflows and in the ocean anyway. So we can use the same central method. So what happens to the model? So one test we did in the early stages was start the model, which has 75 vertical Z levels, start from present day climatology, and then with a low resolution atmosphere, we then spin the ice sheet up for a few hundred years with the climate that we're about to use, the pre-industrial surface mass balance. But the carving point remains fixed, and this was against my original plan, which was to do a double iteration to allow the carving point to move and then continue to spin it up. But that proved to be too complicated. So we only we keep the carving point fixed and see what happens if we then release it after surface mass balance. So this is what happens in a 40-year run. So we have a reasonable surface start condition, and then let it run. Sorry, the date's at the top of the wrong way around. It obviously it goes the other way. I'm not running it backwards. Um, and most of the ice shelves lose mass as a consequence of this spin up. There are some points where it's gaining mass, but they're quite isolated, and this illustrates the need to do an adjustment to the ice sheet, because if you have a big trough or something, or a hole, or spike in the bottom of the ice shelf, it needs to be corrected. So yeah, this adjustment should be going on here, actually. So where does the ice sheet advance and retreat? It's quite small, as you might expect in 40 years, but the grounding line is moving now 20 to 50 kilometers in the ice sheet model, which is not insignificant, but on this plot looks quite small because it's a big scale. So that most of it is advancing, but there's some small retreat in the Amundsen Sea and in the Moni ice shelf. Sorry, the Ross ice. No, yes, Ross ice. Moni ice. No, it's Ross ice shelf. Okay, on the right. Yeah. So there's quite a lot of change on the Ross ice shelf. So it suggests that we need to find a better way to spin the ice sheet up if we're going to go from time zero to projection. But how does the ice sheet shelf melt work? How well is it doing? I mean, there's an initial spin down issue, and this is because at the beginning we just interpolate the out of ice shelf ocean into the cavity, and so for these two warm cavity temperatures to be flushed, it requires this spin up that down of roughly 10 years. Then it sort of equilibrates, but goes into a warm high melt phase. The dotted line, the lines at the right are what the observations indicate should be the right value for the ice shelf melt. And so we spin down to a total value at the top of which is too low, and that although the Filchner-Ronne ice shelf comes out to about right in the end, the Pine Island is slightly too low, and the Ross ice shelf is okay. So some of the ice shelves are doing okay, but other places, mainly the under-resolved ice shelf, are not doing their job. Remember, this is reasonably high-resolution model, so there's quite a lot of ice shelf, which is one good box or so. And this unresolved ice shelf is what's knocking us on the total Antarctic melt. So with a higher resolution model, we'd obviously be able to resolve these ice shelves, but the high resolution models don't perform as well. So it really is a compromise we've got here. So what about climate change? So we
another question
assume,
in the chat.
Oh, yeah. Okay.
And the previous slide, he's asking, can't you tune your exchange coefficients to better match up the observations with where these melt rates end up? I suppose.
Yes, I mean we
do you have a exchange?
We considered this.
Ice shelf?
Yeah. So the exchange coefficient is uniform in these runs, And the reason we did that is that if the exchange coefficient is associated with the roughness of the bottom of the ice shelf, for example, then we don't know that if the bottom melts that we're going to get the same. So if you tune to a specific ice shelf to match observations, then in the future it might do some change. So we didn't want that.
But if you want to have the right number now for the total ice sheet, you could just tune it a little bit to just get the total right, while maintaining it as a constant value. It's not like you know that number.
But if we know that the problem is the unresolved ice shelf, then we could do damage to what's happening in the Filter and Ronnie
but you're not doing a local area model. You're doing a global model, right? And you have to have for the Southern Ocean stratification, you need to have the right amount of melt coming off the ice shelf.
Yeah, the issue then would be to parameterize the unresolved ice shelf so that it comes up.
Yeah, but it's not like your whole system, every single number is perfectly known, right? The exchange coefficients, how fast it mixes into the cavity, what the rates of melt at the bottom of the ice shelf are. All of those things are unknown to a certain degree, right? I mean, you have degrees of freedom. You only need to, if you have one global target or ice sheet wide target, then you only need to change one number, right?
Yeah.
I mean, did you explore that?
Yeah, we did explore that, and actually later on, effectively we did that, and it did change when we started doing our climate change runs. This was really an initial experiment to see that it was producing anything sensible.
Okay, thanks.
We've got Olga in the chat saying that there are physical limits to those coefficients. Yeah, it's a really intriguing problem.
Yeah, but there's still quite a lot of wiggle room.
It may be the best.
But yeah, anyways, please carry on. Yeah.
Yeah, sorry. Please carry
on. Almost come to the end here. So with the climate change simulation, we actually took the CMIP6 scenarios and ran ensembles to look at the change. And although these continent-wide changes show for the high melt SP is 8.5, you actually, even from the beginning, you're beginning to get melt, particularly in the Bellinghausen Amazon Sea. But later on in the run, you're getting very strong melt in the Ross ice shelf, and starting to get in. There's just two example of the ensemble on the right for the high melt scenario. That both of them show Ross ice shelf melting, but one of them shows a bit of Ronnie ice shelf melting. But yeah, so very the reason this happens on the Ross ice shelf is just that the ocean dynamics happens to bring the warm water in at that point. If you shift the winds slightly, or the Ross Sea that generate the Ross Sea gyre, if you shift the winds only slightly, then instead of the Ross ice shelf melting badly, a small one in the Amazon Sea melts badly. So there is, we don't think this is a real thing that happens, that a Ross ice shelf will melt so fast here. But it's just an example of model biases that it happens. The Filton ice shelf, one of the ensemble members shows the Filton ice shelf melting, but another doesn't show it at all. So this probably is structurally well, it's structurally interesting that it isn't a consistent model bias. And when the Ross ice shelf starts to melt depends on the ensemble member as well. So in all ensemble members it happens. So that was sort of interesting because the melt rate is far outweighs any other melt rate. And in the Amazon Sea, you get higher melt rates, and as you'd expect. So the ocean is warming, but the melt rate is still well, at the beginning the melt rate is lower than current day, but it becomes very substantial as you increase it. But these are small ice shelves, the total mass is not great, and the actual movement of the ice sheet in response to these melt rates by 2100 is so tiny. I don't even show a plot of it. So that the ice sheet itself is taking some time to respond to the melt on the ice shelves. But this problem in the Ross ice shelf isn't just a matter for our model. Actually, this shows the popsicles model, and the warm color indicates high melt rate. This is in present day scenario, and so actually the popsicle model is showing very high melt rate in the Ross Sea, the Ross ice shelf, and the Filchner ice shelf as well. So if it across model it's happening, is it just a problem with the models, or is it likely to happen? And we can't rule out that it won't happen. So conclusion. So the model works and is stable, and it covers the atmosphere and the ocean successfully. If we look at the intermediate resolution model, then it has some serious problems that rule it out. That this model would be ideal for its resolution to represent the smaller ice shelves, but the Southern Ocean just isn't good enough for it to do it. It has a warm bias, which is about +4 degrees in the circumpolar current. And then this is symptomatic. Even the UKSM has a slight 1 degree warm bias in the circumpolar current. So a lot of models have this issue, but we're still getting a reasonable representation of the ice shelf melt under pre-industrial conditions. And of course, we're showing, because there's a lot of grid boxes under the large ice shelves, it may well be that these are representing the low resolution model is representing these ice shelves better because they're so big, and we get very strong melt. So what do we do next? Well, round Greenland, we're missing ocean interaction, and that's something in progress at the moment. We'll use a box model to represent the fjords and the plume in the ice shelf ice sheet melt. We need to put together some parameterization for non-resolved ice shelves, and this isn't easy to do because and we may have to use a high resolution model to assess how the parameterization works. And we're missing out on shelf fracture and carving processes. So as I mentioned before, the shelves are static. So if you pretended they were treated, the carving front would retreat with them, and you carve icebergs inside the land mask. And so we really need to change the land mass before we start doing any fracture and disintegration of ice shelves. And this is something that is actually in progress. Robin Smith, our ice sheet coder, is working on this, and it means that the land scheme has to have an adaptive number of grid blocks, which are classified as land, which means that each grid block might be the pointer to a grid box might not be constant. So that's changing, and then that will allow the retreat of the ice front. I mean, there were lots of ideas about how to do this. You could, for example, classify the ice shelf as sea ice, and so that it could retreat and use the land mask that sea ice uses. But all these sort of are halfway points, and so we decided to go the whole route and figure out how to allow the ice shelf to ice front to retreat. And that's it. Thanks for listening.
Thanks very much, Jeff, for a fascinating talk. Oh, Erin says thank you. Do we have any questions from the group? Gavin's got his hand up. Yeah, please, Gavin, go ahead.
Hey, Jeff. Nice to hear from you, actually, after many years. So one of the questions that comes up, of course, in looking at the historical period is to what extent changes in the wind patterns driven by things like the ozone hole have been affecting the upwelling of warm water onto the ice shelves, and therefore perhaps leading to the melt that we're seeing. That's kind of not totally unconnected from changes because of well-mixed greenhouse gases, but is somewhat separate from that. And so given that you now have a working model that has multiple forcings and historical runs, do you have any insight into that?
We do have that capability, in for example, the attribution model can switch switches off on and off the ozone or whatever. Sorry?
I think that noise was someone had the news on in the background or something.
Oh.
Okay.
But we'd have to. The standard model doesn't have ice sheets in, because they increase the runtime by about 25%, and so it's something I'd really like to do. Look at how we can attribute changes to in the ice shelves to different forcings. And I'm particularly interested in the ozone issue.
Do you get a better trend in the Southern Ocean temperature and salinity in the historical period with the coupled model than with the uncoupled model?
Yes, you get. I mean, the feedbacks from atmosphere are necessary to get that, and then we actually improve over the uncoupled model, the representation of change. But the uncoupled, of course, uses historical forcing, and is repeatable in that sense. whereas the uncoupled needs ensembles. The coupled needs ensembles, of course, but the ensemble mean is better than the represents the Southern Ocean better than the uncoupled. Sorry, yeah, coupled. Yeah.
Yeah, that would be interesting to see. Have you got that written up yet already, or is it still kind of all in progress?
Yeah. So all the papers from this are ongoing at the moment. Actually, they've been ongoing for quite a while.
Yes, well, obviously.
We kept on running more runs when we found little bugs and things like that. Yeah, and ensemble members were needed once we made the first discoveries that we appeared to be melting the big ice shelves. But yes, these are in progress of being written up. Probably not until September or so.
We have a question in the chat from Prachi. I'm sorry, I'm not sure if I'm pronouncing your name correctly. Would you like to unmute by any chance and ask a question? It's always nice to hear from people.
Yeah, sure. Sorry, my camera's acting a bit funky, but my question is, when you're calculating the surface mass balance and the surface energy balance from a remote sensing perspective, what are the most important ice surface variables to consider, like land ice or ocean ice? And like also, how do you know or check the accuracy of your surface mass balance and surface energy balance calculations?
So for Antarctica, I mean, most of the balance is in terms of carving and ice shelf melting. There is actually some surface melt, but it's really quite small. And so what we need is the carving rate and bottom melt observations to check. And that, for example, Rignos did this, and that's what we compare against. The number 1500 for the Antarctic total comes from Rigno. And there's different methods, so they all come round about the same numbers. But the icebergs, which we verify against a French guy who measured icebergs, we verify against that and found out it was reasonable. The icebergs are out at sea, that is. The carving rate, we have a very rough idea of. But for Greenland, where there's a lot of surface melt, you can measure surface melt with passive microwave, for example, and occasionally with high resolution imagery to look at the melt ponds. But people don't actually know how much runs off. In some refreezes in the ice and some runs off, and the amount that's running off, nobody really knows.
So then can we rely on remote sensing to tell us how much is runoff, or do we need more ground observations to do that?
Yeah, I mean, it runs off into, obviously on land, it runs off into little rivers, which go to the sea, and almost none of those are measured manually. And I don't think that it's possible for remote sensing to tell us. I mean, the difference in salinity with these rivers running off isn't going to be sensitive enough for SMOS to count. And obviously the plumes come up underneath tidewater glaciers, and occasionally you observe to estimate how much a subglacial melt is, but it's something that's really, really difficult. I have seen a paper on describing, looking at surface plumes with high resolution imagery and estimating how much is emitted, but you really need to have a model of the field to tell you what's going on there. And many. Sorry.
Oh, I was just saying that's very interesting. Thank you so much.
Thanks, guys. We're a little bit over time, so we should probably close out soon and let people go to their next meetings or what have you. I think it looks as if Olga has left. She's probably gone to another meeting or something. I was hoping to reignite that conversation that was going on earlier about, you know, what's the best way to tune your exchange parameters at each ice shelf. But maybe I can chat to you guys offline about that. Yeah, it looked as if she was saying that there's some kind of physical limits that one could use to constrain those parameters. And maybe the best that we could do for each ice shelf is to explore the range of those in sort of like a multi-ensemble run. I'm not sure if you want to say anything on that, Jeff, but it looks like quite a lot of people have left now. I'm rushing off to the next thing. So I think maybe I should just thank you again ever so much for speaking with us today. Yeah, if you can think of anyone else who you would like to see in the series, please let us know. I'm looking forward to uploading.
I couldn't believe it. I kind of asked myself.
Gavin,
Yeah, I just want to say thanks again, Jeff. And I know you've been working on this for like well over a decade, and we're very much in catch-up mode. But we are hoping to learn, you know, the lessons that you've had to learn the hard way, and see if we can't short circuit some of that development process. So we'd be very, very interested in, you know, seeing any of the papers as they're ready to be seen, and to continue this conversation on how to do these things incredibly and yet efficiently. You know, if there are things that you know were a bit of a dead end that didn't end up being important, like, you know, tell us so that we don't go down that dead end too. And you know, kind of issues that arose that weren't anticipated, you know, anything that gives us a bit of a heads up into what we can expect will be appreciated as well. We don't have a huge team working on this. You know, I've got somebody starting in the fall who's going to be the primary person on this. But you know, it's you know, we're not huge, and we don't quite have the resources of the Hadley Center. But we would like to be doing something credible here.
Do you, Gavin? Do you have a landmass that can adapt already?
Yeah, I'm gonna turn on my camera. We've been wanting to have, you know, totally flexible land fractions for a while, for many reasons, and so it's kind of there at the top of our to-do list. But as you're aware, right, it gets complicated very quickly.
Yes.
And so the answer is no, we don't have that functioning yet. But we are very aware that that's a necessary piece of the puzzle to make progress on this.
Yeah, I mean,
I take it then you'd recommend that we get started on that straight away.
Yes, but I know it's. I've been trying to get that done for a decade, and people always want to change the atmosphere, and so you have to play catch up with them.
Is it that the central command at the Hadley Center model does not take your role seriously, or this seriously, or they're just like too busy doing other things?
I think their priorities are other things. But we're moving to a non-structured grid atmosphere fairly soon, and once that happens, it should be easier to do.
I admire your optimism on that. What kind of unstructured grid is it?
It's a yin-yang grid, cubic hexagons.
Cube sphere, no?
Cube sphere, yeah.
Oh, cube sphere, that's not unstructured. It's
well,
like, random triangles everywhere.
No, it's not like the Department of Defense one.
Right, right. But that isn't gonna make your life easier on the landmask issue.
Yeah.
I mean, like the landmask issue for us is, there's so many things baked in the initial conditions that all need to be made interactive to kind of deal with the landmask thing, and it's just like there's 20 different things, and it involves everybody, and getting everybody to do all these things at the same time is hard.
Yeah. But there were lots of false leads we went down, so certainly we can share those with you at some point.
Oh yeah, well, feel free to write down an email all the things that you wasted time on. and we'll try and avoid that. We can waste time on other things. But yeah, I mean, I remember you talking to me about the interactive ice sheets at a visit to the Hadley Center. It had to have been 15 years ago.
Yeah.
but now you have something, which is great. It just goes to show that you need to put in the time and the investment in these things.
Yeah, I mean the resources of the brainy people is always at a premium, and it's them that needed to solve these, and there were a lot of problems.
Yeah, but you feel that you've dealt with them. I mean, you don't have any outstanding, obvious weirdness.
No, we seem to have got things working, and that's what people are particularly happy about.
Yes. And you didn't have any problem with the energy conservation in your ice sheets?
Yes, lots, and there's still an outstanding energy because the ice shelves don't have a temperature, but of course the ocean wants to know the temperature.
Well, of course.
So when you get an iceberg, it's got to have a temperature in order to determine the melting latent heat flux, and things like that are not working. But of course, we don't have a temperature for river water either.
But you have to have an energy for river water, surely.
No.
Really?
It goes in at the temperature of the water it's going into.
Well, how does that conserve energy?
Oh, it doesn't. There's a global adjustment.
So that's an issue that the higher up should fix. I mean, you mentioned earlier, there's nothing more important than conservation. Quite frankly, conservation is the only thing that we know exactly, pretty much. And yet, if we're not doing that, what are we doing?
Yeah, I argue endlessly for conservation because it's a bee in my bonnet. But people in the land scheme, which is run standalone, often don't care about conservation.
But this is the problem of doing development outside of a coupled framework, right? The coupled constraints need to be pushed down to the modules, and they're only important for the coupled situation. They're not important for the modules. And so, but the people at the middle should be forcing those things.
Indeed.
I mean, like, doesn't I mean, I've talked about these things with Catherine. Does she? She doesn't care.
No. I mean, there is a conservation working group, which is run by.
Here's the equation that conserves energy and mass. We're done. We're done. Yeah, I mean, so our problem is that our current atmospheric model is not keeping track of potential energy of condensate, and so and the potential energy term from snow landing on the top of the ice sheet and then falling is actually quite a large part of the energy budget in the ice sheet, and so they assume that there is potential energy, and we don't, right outside. And so we have to do an energy fix up for that, which is very annoying. And then the ice sheet model that we're actually using has decided that the fluxes of ice are so small that they don't need to advect temperature with the ice, and so their advection doesn't conserve heat energy, which is like people, for fuck's sake, like, what are you doing? And and these things are trivial to fix, but it's the same thing. They just don't care. Like, it's small for us, right? But then you say, okay, well, if you melt your whole thing, and then all those energy conservations go away, or misconservations go away, then that's like you're adding like 2 watts per meter squared forcing, which turns out to be important. And they say, oh, there's only 2 watts per meter squared out of 240. Like, no. I find it extremely frustrating. We should have like an international conservation working like protest group to get people to do these things properly. I mean, we're not perfect, but I try and stress these things as much as I can. Okay, cool. Well, thanks a lot, Jeff, and good to see you, and wish you all the best in getting these things done and out there.
Yeah, and I'll let you know what problems we had by an email or something.
Yeah, that'd be great. Yeah, I mean, so keep Craig in the loop. I mean, he's our main liaison on both the sea level, but also the ice sheet and Southern Ocean stuff. I don't know if you've seen any of his talks and things, but we've got some pretty good results from kind of doing a deus ex machina, like putting in the anomalous freshwater off the shelves and improving the Southern Ocean trends quite a lot. But those are like minor issues compared to the big ask. Anyway, but yeah, we're very interested in it. And then that question, the attribution question, like that's a really big one, because there's a lot of ambiguity in how people are attributing the loss of mass on Antarctica to climate change, and there's a lot of details in there that have not there are some dots that have not yet been connected, and so anything that moves us along in that direction, I think will be very welcome.
Yeah. Okay. Well, good to see you again.
Yeah.
I'd like the opportunity to insult you, but
why would you want to do that?
I think Jeff was saying because you're such a lofty person now that it's fun to insult the head of climate change in the current establishment.
Well, feel free.
I got the title is. Sorry, it's rude. Really rude.
You're fired.
Yes, Joe, as Gavin said, I have been doing sort of hosing kind of experiments and interested in how the Antarctic particularly is responding, but also Greenland to more realistic representation of meltwater. And we're working on implementing parameterization initiatives in our model, and I'm working on that myself. So yeah, any information, things that have gone well and badly for you would be great if you're willing to share.
I'll show. Like, do you want to see a picture? I'll show you a result, hot off the press, as it were.
But if you're going to do ice sheets, Greenland is supposed to do, and it's easy.
Yeah, it doesn't make any difference though.
But certainly this hypsometry, subgrid hypsometry is very useful.
Yeah, so we have we've called them elevation classes, and so we've been doing that for a while. So that's already in there, and so that, I agree, that was a big thing. The big problem that we have though is distributing precipitation across the classes. Yeah. So you can do snow to, but you've got this energy conservation issue. You can't have it like, you're losing snow here, but then then it melts and it's rain here, because then where does latent heat go? So there's some issue about the precipitation, and of course the precipitation does not fall equally on all the different elevations, right? So there's a lot less of it up here than there is down there. So working out a way to do that sensibly has been a challenge. But I'm just going to show you. I'm going to show you one little thing. So this is Craig's work. So I hope you won't mind me showing you.
While you're digging out.
Yeah, I don't know why. Can I not share from?
You should be able to. Share screen down there.
Yeah, I'm doing it from the browser. Is that not allowed?
Yeah, that's what I'm doing it from. So it works.
Yeah, where is the setting to do share screen? How do I do share screen?
Up somewhere.
Up at the top.
So you're.
That's our car.
In an internet browser. I'm not sure. Yeah, Jeff, if there's any, thanks again for talking. If there's anyone else in your group that you think,
yeah, I can't see how to do it from here. Sorry.
Good to get speak, then by all means let us know. Great to hear from you. So did you and Gavin used to work together? Presumably, Gavin, were you?
No. I mean, I've over the decades, I've done various visiting things at the Hadley Centre. I spent a month there when it was when it was in Bracknell, and then again in when it was in Exeter more recently.
Yeah, you've done the visiting scientist thing, haven't you?
I'm gonna go get it.
Apparently, I have to go. Oh, okay. I have neglected my 5-year-old daughter at camp. Hold on.
What was the plot that you wanted to show?
I was going to show the one that I made with the temperature trends.
Yeah, I can show that.
Yeah, you can show that. Okay, you try that. But hold on, I need to. Yeah, no. Are you sure, Sarah? Okay, Sarah's not. Okay, we're both negligent. Yeah.
I can't remember how long ago I visited GIS.
Oh yeah. Well, maybe there was a sea ice workshop. Were you at that?
Yes. Yeah.
Oh yeah, that was in like 98 maybe.
Yeah, 98 maybe. Yeah.
Which screen can you see? Can you see?
I can see your I can see your whole desktop, and so.
No, but which desktop I've got two? Can you see?
Oh well, the one with the zonal mean surface temperature trends.
Okay, so I've got the right one up.
Yeah.
Okay, good. This was the figure that you wanted to show, right?
Yeah.
And so what in this run is I kind of like sort of hack the model in such a way so as to allow us to more accurately represent the recent trends in meltwater forcing from the Antarctic and Greenland. And this is the result that we get from this. So I essentially just added meltwater around Antarctica and Greenland, along with observations where Antarctica is both from the grounded ice sheet and from the ice shelves. And the blue line here shows the historical simulations without meltwater forcing. The red line shows it with, and the black line here shows its temp observations. And this is zonal averaged temperature trend. And as you can see, in the runs where we have meltwater forcing, the trend is much better, particularly in the Southern Ocean.
Yeah, a little bit around Greenland too, but it's not so noticeable. But if you look at the whole of the CMIP ensemble, which Craig has looked at, it looks like our ensemble, right? So it looks like the blue lines, and you don't get anywhere where there's net cooling, and so the anomalous freshwater is certainly of the right order of magnitude to do this, and is kind of key, at least in our runs. If you've done something similar, I'd be very interested to know what your results were.
Yeah, when we put melting of icebergs, and initially when we put Lagrangian icebergs in, they melted only melted. They didn't put the latent heat in, and when they put the latent heat, you got when I pressurized them to do it, and the latent heat dropped the temperature of the Southern Ocean by a good half a degree. So, but yeah, I'll have to have a look, because of course all our models have melt from Antarctica in now, so we don't have one where you turn off the latent heat, or looked at the trend even. I don't think we've looked at the trend. I don't know how much extra ice shelf melting you're putting in here.
So in the latter years, when all these things are combined, you have something like the maximum it tops out at is 750 gigatons per year, which is on the upper end of everything added together. But it starts out at essentially something like 200 gigatons per year, around about the sort of like mid-1990s. It ramps up quite quickly, and I think the rate of change is actually also quite important. There's that paper by Paulin which suggests that the impact is larger for an accelerating increase rather than an abrupt sudden.
Yeah, so sea ice is going to increase.
Yeah, I mean, so that's the result that we get from these kinds of experiments, that you see an increase in sea ice, particularly for higher forcings, and that drives an increase in albedo, and it begins to have an impact on the water vapor feedback. So in very high melt cases, you end up with surface cooling or a slight mitigation of the global warming trend. However, the absolute magnitude of these things is still something that we need to, it is a point of further research. So in the case where you have, really wild Antarctica melting, you do Conto and Pollard kind of 2 meters by 2100 or what have you. You have quite a significant global cooling impact relative to the global warming trend.
Yes, yeah. I've been on a paper representing that, a Conto and Pollard freshwater increase. I don't know if you've seen it. Shona Mackay led the paper, and that looked at the effect of freshwater mostly on sea ice, but the effect spreads to the equator.
Yeah, it's a fascinating problem. How all of these processes are going to interact over the next 100 years is really interesting and challenging. And there's just so much to do. And there was this nice quote from, who was it? The high resolution modeling guy saying, you know, there's more than many careers worth of development still to be done in the Antarctic Shelf Sea, trying to disentangle all these processes and how they're going to interact over the next century. It's very clear that, at least from our work, it suggests that meltwater forcing has an important impact both on regional and global trends. I'm rambling, guys, sorry.
What was that paper that you just referred to?
Lead author was Shona McKay.
M-A-C-K-A-Y?
M-A-C-K-I-E. And I think it was in climate dynamics.
Is she from New Zealand?
Yes.
Okay, got it. Okay, thanks.
What was her second name again? Sorry, M-A-C-K-I-E. I-E. Oh, yeah. I think I've read something by MIT.
So there's one paper where we look at the pre-industrial control and fresh water, and another where we put climate change in. So the impact is slightly cooling, like similar to yours.
Yeah, she hasn't updated her website since 2018. Kind of annoying.
No, she works in Bergen Sea Ice Group at the moment. So.
Oh, okay. Well, this could explain why that website is not done. Right. Okay. All right.
There was a bit of an odd effect.
Found the data. No, hold on. Where is it? Oh, it's in. Okay, there we go. There we go. That was harder to find than I thought it would be.
Yeah. But yeah, there was an interesting effect from putting fresh water in 100 years later. We got a cooling in the Arctic, which was statistically significant. And I wasn't sure whether it was due to Rossby waves or because the water takes longer to get up there.
Yeah, no, it had to be an atmospheric connection.
Yeah.
Yeah, no, that's not the right one. Here, here's the link. All right, that's yeah. No, we'll look into that. Great.
Oh, yeah, I got it. Thanks.
Yeah. Whew. That's right. That's a lot of meltwater flux that you put in there.
Yeah. We the guy who's replaced her is trying with realistic amounts of meltwater, but
yeah. So that's what we've been trying to do. I mean, we've been trying to get, like, you know, what would you do if you just wanted to have this as an additional historical forcing? So
he's now putting in the results from our ensemble of ice sheet models, which and then putting that in into a ensemble, because it's such a small amount. You need to create an ensemble to see what the statistically significant changes are.
But you have to do that with the coupled runs anyway. I mean, it's not. I mean, everybody's running like nobody's doing single historical runs anymore. I mean, like everybody's doing like 10, 20, 30 note runs.
Yeah,
so
yeah.
That's not. We have to get over that. We just have to accept it. Okay.
Yeah,
I have to A, apologize to my daughter for abandoning her, and B, go on to my next meeting. So I will call this quits. But thank you very much for the talk and for the chat. And we will see you again in person sometime soon, hopefully.
Well, indeed, and I can insult you to your face. Right.
I look forward to it.
Okay. Cheers.
Okay.
Thanks.
Bye.
Thank you.